So in section 5.2, we talk about infinite series. Now, let's be clear. A sequence is a list. Here we're going to be explaining the meaning of the sum of an infinite series. A series is a sum of elements in a list. Okay, so if you recall, a sequence is a list. All right, so that looks like A1, A2. Lists are separated by commas. And you can determine whether or not a sequence has a limit. That's what we have done. Now we want to talk about a series. These function differently. Okay, so we can take the items from a list and add them up. And get what we call a series. Okay, so a series is a sum. All right, so now let's say I have a sequence of terms, okay? And I want to sum up the first n. So let's sum the first n terms of a sequence. So I'm only going to sum n of them. And I'm going to call that thing Sn. Sn is going to be A1 plus A2. And I'm going to go all the way up to An. And this is called the nth partial sum. The reason why it's called the nth partial sum is because I'm only summing n terms. I'm not summing all of them. So here's an example. So let's consider the sequence where An is equal to 1/2 to the n minus 1 power. Okay. Well, we know then that An this looks like 1, 1/2, 1/4, 1/8, 1/16. That's the entire sequence. It is a list of the numbers that are powers of 1/2. Sn, so let's look at S1. So S1 says, take the first term. S2 says take 1 plus 1/2. Okay. Now 1 plus 1/2 is 3/2. And I can conveniently write that 3/2 is 2 minus 1/2. What is S3? S3 is 1 plus a half plus a fourth. So that thing is 7/4. I can conveniently write 7/4 as 2 minus 1/4. S4 is 1 plus a half plus a fourth plus an eighth. And that equals 15/8. I can conveniently write 15/8 as 2 minus 1/8. Okay, so I'm developing a pattern here. This is 2 minus 1/2 to the first power. This is 2 minus 1/2 squared. This is 2 minus 1/2 cubed. So notice this is a 4. 2 minus 1/2 cubed. This is a 3. 2 minus 1/2 squared. This is a 2. 2 minus 1/2 to the first power. I can conveniently write this as 2 minus 1/2 to the 0th power. How's that? Okay, so now if I keep going, I get Sn. Sn is going to be 1 plus 1/2 plus 1/4 plus, I'm going to go all the way up to the nth term. The nth term has a pattern, it's a form. It is 1/2 to the n minus 1. Okay. And I can conveniently write that as 2 minus 1/2 to the n minus 1. So in this example, the nth partial sum is 2 minus 1/2 to the n minus 1. Now guess what? If I sum the whole series, that would be summing everything on out to infinity. Well, that would look like the limit as n goes to infinity because I'm summing all the terms that go to infinity. So the first thing I want to do is I want to give you a notation. So Sn by definition for all the series, Sn is going to be this notation, the summation. That means sum up. K equal 1 to n of whatever AKs we have. Now the sum of the series, the total sum, S, which is the sum, n equals, K equals 1 to infinity of AK, is the limit as n approaches infinity of the sum K equal 1 to n of AN. Okay, so if I let n go to infinity, I get the sum to infinity. This should be AK. So that means, or that implies, that the sum of the series is the limit as n goes to infinity of the nth partial sum, because that's what this is. So for this series, so given the sum n equal 1 to infinity of an, this is the limit as n approaches infinity of Sn, but that's just the limit as n approaches infinity of 2 minus 1/2 to the n minus 1. And as I keep taking powers of 1/2, this goes to 0. So therefore the sum of that whole series is 2. So this is the problem. So this is what we're working with. Okay, so let sum an be a sequence. That is a list of numbers. If the sum k equal 1 to infinity of ak is equal to some number L, then the sum of the terms, then the series converges. Okay. If the sum k equal 1 to infinity of ak is equal to infinity, then the series diverges. Okay, so here's the difference, and this is the big key. We can look at a list of numbers and see if they start to look like something, or they are converging to a number. That is the convergence of a sequence. When we talk about the convergence of a series, we want to know if I sum up all the terms, do I get something finite? Okay, so if we sum all the terms, do we get something finite? Okay, so here is our first series test. Number 1, geometric series. So a geometric series has a certain form, okay? A geometric series looks like the sum n equal 1 to infinity of a r to the n minus 1. What does that mean? When n is 1, I get a. When n is 2, I get a times r to the first power. When n is 3, I get a times r squared. When n is 4, I get a times r cubed. And we keep doing this, ar to the n minus 1. So this is a geometric series. It is the sum of all of these terms. Okay? So the one we just did was a geometric series. So for example, the sum n equal 1 to infinity. I'm gonna let a be 1. So I'm just going to get 1/2 to the n minus 1. We already know that when we're going to get 1 plus 1/2 plus 1/4 plus 1/8 plus dot, 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 plus 1/2 to the n minus 1 plus dot, dot, dot. And we already know that if we sum that whole thing, we're just going to get 2. That one we've already figured out. Here's another one. The sum n equal 1 to infinity of 2 times minus 1/4 to the n. Well, they're all going to be multiplied by 2. So I'm going to pull the 2 out. I'm going to get 1 when this is n minus 1. So when n is 1, I get negative 1/4 to the 0 power, that's 1. When n is 2, I'm going to get minus 1/4. When n is 3, I'm going to get positive 1/16. Then I'm going to get negative 1/64. And then I'm going to get positive 256, I think. Plus minus 1/4 to the n minus 1 plus dot, dot, dot. Okay. All right. So I want to show you that we can actually find the sum of this geometric series. Okay. So let's let r equal 1. So if r equals 1, I get Sn is equal to, so if r equals 1, I get the sum n equals 1 to infinity of a, and r is 1, so I just get 1 to the n minus 1. So I just get this sum. Now that's a problem. Let's see what we get. The nth partial sum is going to give me a plus a plus a plus a, and I'm going to do this n times. So the nth partial sum is going to give me n times a. So if I take the limit as n approaches infinity of the nth partial sum, that's the limit as n approaches infinity of n times a. Well, if a is positive, this is going to give me positive infinity if a is positive, and negative infinity if a is negative. So summing a number, just the same number over and over again, goes to infinity. That doesn't work. Okay. All right. So now let's try to figure out what the actual sum of this thing is. Okay. So can we find S equal to the sum n equal 1 to infinity of a r to the n minus 1? Can we actually find what S is? Oh, that should be a question mark. Okay. So let's see if we can find that. All right, so first we're going to let Sn is equal to the sum up to n. We already know the nth partial sum is equal to a plus ar plus ar to the n minus 1. Uh-oh, I done skipped all the way to the end, guys. Plus ar squared plus dot, 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 all the way up to ar to the n minus 1. So let's multiply that by r. So r times Sn is going to be ar plus ar squared plus ar cubed all the way up to A, and then I'm going to multiply R to the n minus 1 by R. So I'm going to get that. So now I'm going to subtract them. So Sn minus Rsn is equal to, well, if I take the top row, if I take this and subtract that, all the middle terms are going to subtract out. The AR, this will subtract that, this will subtract that, and everything will subtract. And the only thing I'm going to be left is going to be A minus A R to the n. So let's factor out Sn over here. So I get Sn times 1 minus R is equal to A times 1 minus R to the n. So now I know that Sn, the nth partial sum of the geometric series, is A times 1 minus R to the n over 1 minus R. Now, let's take R to the n. If R is like 2, 2 to the n is going to get humongous as n goes to infinity. So I know R can't be 2. In fact, R can't be anything whose absolute value is 1 or more. So we say if R, the absolute value of R is less than 1, then the limit as n approaches infinity of R to the n will be 0, because I'm multiplying a fraction times itself and it's just getting smaller and smaller. So therefore we get the limit. So the sum of the series S, which is the limit as n approaches infinity of the nth partial sum Sn, is the limit as n approaches infinity of A times 1 minus R to the n over 1 minus R. Well, this term is going to go to 0. So I just get A over 1 minus R if the absolute value of R is less than 1. Okay, so I know that seems a little bit much, but it all breaks down to the following. Nice and simple. For a geometric series, the sum n equal 1 to infinity of AR to the n minus 1, I know the sum of this series is going to be A over 1 minus R if the absolute value of R is less than 1. And the sum n equals 1 to infinity of AR to the n minus 1 diverges if the absolute value of R is greater than or equal to 1. Okay, nice and simple. All right, here we go. So here's your first geometric series. So we have the sum n equals 1 to infinity of 1/2 to the n minus 1. Okay, A is 1 and R is 1/2. So the absolute value of R is less than 1. So I know this series is going to converge. And in fact, it's going to converge A is 1. It's going to converge to 1 over 1 minus R is 1/2. So that's 1/2. And by golly, that's equal to 2, which is what we got before. Okay, let's look at the sum. N equals 1 to infinity of 1/5 times 7/10 to the n minus 1. Well, A is 1/5 and R is 7/10. So this is 1 minus 7/10. So this is 1/5 divided by 3/10, which is 1/5 times 10/3. So this converges to 2/3. Okay, I'm okay with that. Number 3, summation n equals 1 to infinity of 3 times 1 9/8 to the n minus 1. Well, I can automatically say this diverges because the absolute value of R, which is the absolute value of 9/8, is bigger than 1. Done. Don't even have to do anything. If that number R is bigger than or equal to 1, it diverges. You can only have a sum when the absolute value of R is less than 1. And it works with negative numbers. The sum n equal 1 to infinity of 1/2 times negative 1/3 to the n minus 1. I can see here that A is 1/2 and R is negative 1/3. So this is going to be 1/2 over 1 minus, and I have to put in negative 1/3. I hope everybody sees that. Okay, so it's negative 1/3. That's what R is. That's what goes in here. So this is 1/2 over 1 minus 1/3 is 2/3. No, 1 plus minus negative, that's 4/3. So I get 1/2 times 3/4. So this converges to 3/8. All right, here's one for you guys to do. What does that geometric series sum to? Hello? I'll let you guys do that. I wasn't recording. I completely forgot that I was not recording it. So I don't even remember where I stopped recording. I stopped recording here. Ugh. Okay, let me go back. Thank you. All right, so I had stopped recording. I forgot. We figured out, oh, this answer was not 3/25. It turned out to be 1/3. Okay, because we put in 1/5 and 1 minus 2/5. Okay. Then we started the telescoping series and we actually completed this one. We said we had the sum of 1/n minus 1/n plus 1. And we said we looked at the nth partial sum, which says sum the first n of them. We wrote them out. This is the k equals first term, k equals 2 second term, k equals 3 third term, all the way at the k equals n term. Then we reordered them. And when we reordered them, we saw that the middle terms all dropped out. We got Sn is equal to 1 over 1 minus 1 over n plus 1. And then we took the limit of the nth partial sum and we got 1. And then we went back and put that in. Okay, so then we started a new example. And for this example, we need to start at n equals 2 because at n equals 1, it blows up. So this has to be n equals 2. And we had something that looked like that, and we don't know what to do with that. So the best thing to do is to figure it out in partial fractions. And I'm still stuck on the fact that nobody can tell me what I called that thing. I called that thing the major equation. Okay, so we put in n equals minus 1, and we get 1 is equal to b times minus 1. So b is equal to -1/2. And we put in n equals +1, and we get 1 is equal to a times 1 plus 1. So a is equal to +1/2. Okay. So therefore we get that the sum n equal 1 to infinity up n equals 2 of 1 over n squared minus 1 is the same as the sum. We can pull the 1/2 out now. Well, let me put the other step in. So that's the sum n equals 2 to infinity of, now we split it up like this and wrote 1 over n minus 1, n plus 1. And we can write it in partial fractions. A and B are both 1/2. So we get 1/2 the sum n equals 2 to infinity. And the first one is 1 over n minus 1. And then b was negative, so it's 1 over n plus 1. Good. Okay, so what does the nth partial sum look like? Sn is 1/2. The first term is going to be 1 minus 1/3. The second term is going to be, when we put in 3, 1/2 minus 1/4. Then the next term, we put in 3, 4, we're going to get 1/3 minus 1/5. And the next term will be 1/4 minus 1/6. Okay, and I guess we will be finishing this on Monday because tomorrow you have recitation, Thursday you have an exam. Okay.